enzyme catalysis. So what do you mean by catalysis? And catalysis means the increase in the rate of reaction by using a catalyst. That is called catalysis. Okay, the increase in the rate of reaction by using a catalyst. Increase in the rate of reaction, okay, by using a catalyst, that is called catalysis. Already we discussed why rate of reaction increases and if you use catalyst. Activation energy required for the reaction decreases. If you use catalyst, what happens? Reaction proceeds by a new path where activation energy required for the reaction decreases. That's why rate of reaction increases. That phenomena is called catalysis. Okay. Now enzyme if you use a catalyst, that is called enzyme catalysis. Enzyme catalysis comes under homogeneous catalysis or heterogeneous catalysis. Enzyme catalysis comes under homogeneous catalysis. It is an example for what? Homogeneous catalysis. Enzyme catalysis is an example for homogeneous catalysis. Acid base catalysis also. Acid base catalysis, enzyme catalysis comes under what? Homogeneous catalysis. Homogeneous catalysis means reactants and catalyst both are in the same phase. If reactants and catalyst are in the same phase, all are in the same phase, then such catalysis is called homogeneous catalysis. If reactants and catalysts are in different phase, that is said to be heterogeneous catalysis. For example, we discussed decomposition of hydrogen iodide on gold surface. Hydrogen iodide gas, gold solid. Okay, decomposition of hydrogen iodide on gold surface, that comes under what? Heterogeneous catalysis. Here we are studying kinetics of homogeneous catalysis, that is enzyme catalysis. Kinetics of heterogeneous catalysis we study at surface chemistry. And at surface chemistry we study kinetics of heterogeneous catalysis by using Langmuir adsorption isotherm. That is also very important. And Langmuir adsorption isotherm, that explains what? Kinetics of heterogeneous catalysis. Okay. So here enzyme catalysis is an example for homogeneous catalysis. Enzyme is nothing but what? That is a biomolecule or high molecular weight organic compound. High molecular weight organic compounds produced by living organisms. So enzymes are nothing but they are biomolecules or high molecular weight organic compounds. They are produced by living organisms. Okay, they catalyze many biological reactions, right? Some examples if you see for enzyme catalysis reactions. Okay, in our body many reactions are catalyzed by enzymes. Okay, some of the reactions if you see sucrose, decomposition of sucrose to glucose and fructose. Some examples I am giving for our enzyme catalysis reactions. Sucrose to glucose and fructose, that is catalyzed by which enzyme? Andi? That is catalyzed by an enzyme, that is invertase. Invertase, an enzyme that catalyzes conversion of sucrose to glucose and fructose. Glucose to ethyl alcohol, which enzyme catalyzes and this conversion? That is gymase. Conversion of urea to ammonia. Okay. Conversion of urea to ammonia and CO2, that is catalyzed by an enzyme, that is urease. For example, conversion of milk to curd, lactobacilli, that converts milk to curd, that is catalyzed by lactobacilli. Next, proteins to peptides, that is catalyzed by an enzyme, that is pepsin. Pepsin is an enzyme that converts proteins to peptides, proteins to amino acids. Okay, that is catalyzed by what? Trypsin. Okay, like this, so many enzyme catalysis reactions we have. Okay, these are some of the enzyme catalysis reactions. Proteins are converted to peptides by an enzyme, that is pepsin. Proteins are converted to amino acids by an enzyme, trypsin. Okay, so catalysis is nothing but increase in the rate of reaction by using a catalyst, that is called catalysis. By using catalyst, what happens? Activation energy of the reaction decreases. This question given in many exams only. Activation energy of the reaction decreases. Why rate of reaction increases? By using catalyst. Okay. Next, enzyme catalysis comes under homogeneous catalysis. One more example for homogeneous catalysis, acid-base catalysis. Okay, enzymes are nothing but they are biomolecules or high molecular weight organic compounds. They are produced by living organisms. They catalyze many biological reactions in our body. Okay, these are some examples. Next, mainly we have to study what? Kinetics. That is important. Okay, kinetics is important here. Now, of enzyme catalysis reactions. Kinetics of enzyme catalysis reactions. Kinetics of enzyme catalysis reactions depends on what? Kinetics of enzyme catalysis reactions depends on what, if you see? So that depends on concentration of substrate, temperature and pH. Concentration of substrate, temperature and pH. That's why our body has to be maintained proper temperature and proper pH. Then only all organisms work properly. They function properly, right? So proper temperature and proper pH has to be maintained. Okay, so kinetics of enzyme catalysis reactions depends on what? Concentration of substrate, pH and temperature. So in this, how kinetics changes with the concentration of substrate? How kinetics changes with concentration of substrate, that is explained by a mechanism, that is Michaelis-Menten mechanism. Important mechanism, that is Michaelis-Menten mechanism explains what? How kinetics of enzyme catalysis reactions depends on concentration of substrate. That is explained by Michaelis-Menten kinetics only. Write that point. Kinetics of enzyme catalysis reactions. Kinetics of enzyme catalysis reactions. Kinetics of enzyme catalysis reactions. Kinetics of enzyme catalysis reactions with the concentration of substrate. With the concentration of substrate. With the concentration of substrate is explained by Michaelis-Menten mechanism or Michaelis-Menten kinetics. Kinetics of enzyme catalysis reactions with concentration of substrate is explained by Michaelis-Menten mechanism. Okay, now we have to see Michaelis-Menten mechanism. Put heading Michaelis-Menten mechanism. Michaelis-Menten mechanism. Next one, you add one point and enzyme catalysis reactions are specific or non-specific and enzyme catalysis reactions are highly specific and they are highly specific. For example, urease can catalyze only conversion of urea to ammonia and CO2. Gymase can catalyze only this reaction. Pepsin can catalyze only this reaction. Okay, so therefore enzyme catalysis reactions are said to be highly specific compared to other reactions, other catalysis reactions. So the enzyme catalysis reactions are highly specific. Okay, next one, Michaelis-Menten kinetics. So I am taking a enzyme catalysis reaction and that is substrate plus enzyme gives rise to product. Substrate plus enzyme gives rise to product. So now what is the mechanism proposed for this reaction? Simple mechanism proposed, that is initially enzyme and substrate combines to form a complex, that is enzyme substrate complex. Initially enzyme and substrate combine to form enzyme substrate complex, which further decomposes to give product, and again enzyme released. Whether enzyme involves in the reaction or it doesn't involve in the reaction. It doesn't involve in the reaction. Catalyst doesn't involve in the reaction. Okay. This is the simple mechanism proposed by Michaelis-Menten for enzyme catalysis reactions. Enzyme plus substrate combine to form enzyme substrate complex, which further breaks to give product. The rate constants given as K1, K minus 1 and K2. Rate constants we are taking as K1, K minus 1 and K2. Okay. For the formation of enzyme substrate complex, briefly I am explaining. For the formation of enzyme substrate complex, there are two proposals and two theories. And for the formation of enzyme substrate complex, we have two theories. One is what? Fischer's, right? Fischer's lock and key model. There are two theories which explains the formation of enzyme substrate complex. One is Fischer's lock and key model. According to this model, enzyme is considered as lock, substrate is considered as key. Enzyme is lock and substrate is key. According to this model, enzyme possesses fixed structure or rigid structure. According to this model, enzyme possesses which type of structure? Fixed or rigid structure. Whether its structure is flexible or not flexible, and not flexible. Its structure is fixed. Okay, a proper key can only open a particular lock. Okay, a particular key only open a particular lock. Similarly, a particular substrate only can fit into the active site of enzyme. A particular substrate only can fit into the active site of enzyme. So during formation of enzyme substrate complex, during binding of enzyme and substrate, is there any change in the structure of enzyme or no change in the structure of enzyme? No change in the structure of enzyme. The substrate which fit into the active site of enzyme, such substrate only forms enzyme substrate complex. Okay, the substrate which fit into the active site of enzyme, such substrate only forms enzyme substrate complex. During the formation of enzyme substrate complex, no change in the structure of enzyme. No change in the structure of enzyme. That is called Fischer's lock and key model. And another theory we have, that is Koshland's induced fit hypothesis. Koshland's induced fit hypothesis. According to this model, enzyme possesses which type of structure? Enzyme possesses flexible structure, non-rigid structure. So that means its structure may changes according to the shape of substrate. Its structure may changes according to the shape of substrate. Okay. So during binding, the shape of enzyme may changes. During binding or during formation of enzyme substrate complex, the shape of enzyme may changes. That is Koshland's induced fit hypothesis. Okay. So these are the two theories which explains the formation of enzyme substrate complex. Okay. Now we have to see kinetics. Okay, I am going to kinetics part. Now if you write rate of product formation, rate of product formation. What is rate of product formation? Which step product is forming? Second step product is forming. So V is equal to what? K2 into concentration of ES. Let us consider that is equation 1. What is ES? whether it is reactant or product or intermediate and intermediates. How to get the concentrations of intermediates? By steady state principle, okay, or steady state approximation. So according to steady state approximation, the change in the concentration of intermediate with the time is equal to what? 0. The change in the concentration of intermediate with the time is equal to 0. Net change is 0. In which steps ES is involved and in the forward reaction, whether ES is involved or not? Yes, ES is forming. In the backward reaction, ES consuming. In the second step also ES consuming. In the forward reaction, ES forming. So which sign we will get? Plus sign. What is the rate of formation and K1 into E into S. In the backward reaction, ES is consuming. So minus K minus 1 into ES. Next, in the second step also ES is consuming. So minus sign. Rate of consumption K2 into ES, that is equal to 0. Okay. Next, if you see, if initial concentration of enzyme if you consider as E naught, if you consider initial concentration of enzyme as E naught, so in that some of the enzyme may undergo binding with substrate. Some of the enzyme may undergo binding with substrate to form enzyme substrate complex. So some of the enzyme exist in the form of enzyme substrate complex. The remaining may be unreacted enzyme. So the initial concentration of enzyme we can write with respect to ES as ES plus E. Now here we need what? E, and here we are converting concentration of E also into ES terms, and we are converting concentration of E also into ES terms. So concentration of E we can write as E naught minus ES. E naught minus ES. Concentration of E is equal to E naught minus ES. Okay. So now you substitute that, and in the place of E, if you substitute E naught minus ES, directly I am writing K1 into E naught into S, we will get minus K1 into ES into S. K1 into E naught into S, K1 into ES into S. So we get K1 into E naught into S minus K1 into ES into S. K1 into E naught into S minus K1 into ES into S, right? And minus K minus 1 into ES minus K2 into ES. If you bring all the ES terms to right side, we want to get the expression for concentration of ES. Okay. Bring all the ES terms to right side and take concentration of ES common. So K1 into concentration of E1 into S is equal to concentration of ES into K1 into S, K1 into S plus K minus 1 plus K2. And final expression for concentration of ES, K1 into E naught into S by K1 into S plus K minus 1 plus K2. That is the expression for concentration of S, or we can write like this also. If you divide numerator and denominator with K1, if you divide numerator and denominator with K1, we get E naught into S by K1, K1 gets cancelled, concentration of S plus K minus 1 plus K2 by K1. All those are constants, all those constants are taken as Km, where Km is equal to what? K minus 1 plus K2 by K1. We are dividing numerator and denominator with K1 and Here K1 gets cancelled. Here also K1 gets cancelled. Here we are getting K minus 1 plus K2 by K1. That we are taking as Km. That is called as Michaelis-Menten constant or Michaelis-Menten coefficient. That is called as Michaelis-Menten constant or Michaelis-Menten coefficient. Okay, now final equation, rate equation from 1. So from 1, the rate equation is V is equal to K2 into concentration of ES, that is E naught into S by concentration of S plus Km or Km plus concentration of S. This is the final equation. V is equal to K2 into E naught into concentration of S by Km plus concentration of S. So to convert E to ES terms, we didn't write directly, we didn't write directly the concentration of ES, similar to rate of formation by rate of consumption. Like that we didn't write directly, since to convert E to ES terms. So just you remember what is the expression for enzyme substrate complex concentration and final rate equation. Let us consider this is equation 2. Now you verify what is the kinetics of enzyme catalysis reactions at high concentration of substrate and low concentration of substrate. You may verify at high concentration and at low concentration. You write that. Two cases you write, at high concentration and at low concentration. Two cases, one is at high concentration, at high concentration of substrate, and the second one at low concentration of substrate. At high concentration of substrate, which can be neglected, and Km can be neglected compared to S. Km can be neglected compared to S. So Km plus S we can write as S. Km can be neglected. So from 2 we get V is equal to K2 into E naught into S by S. SS gets cancelled. SS gets cancelled. So we are getting K2 into E naught. We are getting K2 into E naught. So the rate obtained at high concentration of substrate is high. At high concentration of substrate we will get maximum rate. That's why this K2 into E naught is also called as V max. And K2 into E naught is also called as what? V max. So therefore it follows which order kinetics, and at high concentration of substrate, is there any expression for concentration of S, and there is no expression for concentration of S. So V is independent of concentration of substrate. V is independent of concentration of a substrate. That means it follows zero order kinetics, and so therefore it follows zero order kinetics. At high concentration of substrate, enzyme catalysis reactions follows zero order kinetics. Okay, so from this, the expression for rate we can also write as V is equal to K2 into E naught. We can write as what? V max. Okay, V is equal to, we have this one, K2 into E naught into S by Km plus S. This also we can write as V max into concentration of S by Km plus concentration of S. K2 into E naught we can write as V max. So from this, the expression for V by V max, concentration of S by Km plus concentration of S. The importance of V by V max is, this is rate at a particular situation. This is rate at high concentration of substrate. Okay, maximum rate. So this V by V max indicates fraction of reaction completed. Fraction of reaction completed at a particular concentration of substrate. At a particular concentration of substrate, what is the fraction of reaction completed, that is given. So V by V max indicates fraction of reaction completed. This is at high concentration of substrate. Next you write at low concentration of substrate. Second one, at low concentration of substrate. At low concentration of substrate. Now Km plus concentration of S, which is neglected, and now concentration of S can be neglected compared to Km. So Km. So from 2 we get V is equal to K2 into E naught into S by Km. Therefore, what is the relation between rate and concentration of substrate? Rate is proportional to concentration of substrate power 1. That means enzyme catalysis reactions follows first order kinetics at low concentration of substrate. So enzyme catalysis reactions follows first order kinetics at low concentration of substrate. Okay, so you remember the expression for final rate equation. And what is V max? V max is nothing but K2 into E naught. And what about order at low concentration and high concentration? At high concentration, all the enzyme may be saturated with a substrate. That's why further with increase in the concentration of substrate, no increase in the rate of reaction. That's why it follows zero order kinetics. Okay, so therefore, based on this equation, if you plot a graph between rate of enzyme catalysis reaction and concentration of substrate, at low concentrations, if concentration of substrate is increased by 2 times, rate also increases by 2 times. If substrate concentration is increased by 3 times, rate also increased by 3 times. It follows first order kinetics. So this type of graph we will get at low concentrations, and at high concentrations it reaches a maximum rate. Zero order. At high concentrations, what we will get? Zero order. This is nothing but V max, maximum rate. It reaches maximum rate. Okay, at low concentrations, V is proportional to what? S power 1. At high concentrations, V is proportional to what? S power 0. Concentration of S. Concentration of S, you write. Concentration of S power 1. Concentration of S power 0. So at intermediate concentrations, it may be in between 0 and 1. At intermediate concentrations, it may be in between 0 and 1 order. If you take a particular situation, that is, if concentration of S is equal to Km, then what about rate? If concentration of S is equal to Michaelis-Menten constant, then what about rate? if you see that if concentration of S is equal to Km, okay, then this is the equation we have. V is equal to V max into concentration of S by Km. In the place of Km I am writing concentration of S. So concentration of S plus concentration of S. 2S we are getting. SS gets cancelled. So therefore V is equal to what we get? V max by 2. So that means if concentration of S is equal to Km, then V is equal to what? V max by 2. So we'll get half of the maximum rate. V max by 2. V max is nothing but what? K2 into E naught. So K2 into E naught by 2. So if concentration of substrate is equal to Km, then rate obtained is nothing but half of the maximum rate. This question given last time tsgenco only. In CSR also given 4 marks question based on this concept. Based on this concept, one 4 marks question given. In tsgenco direct question given. Okay. So we derived rate equation, applied at high concentration, low concentration, and we considered a particular situation. If concentration of substrate is equal to Km, then rate obtained is nothing but half of the maximum rate. So here we are getting a linear plot or non-linear plot, and non-linear plot we are getting. So next we have to see linear plots for enzyme catalysis reactions, and okay, that we'll see after a break. Okay, right? Take a break and